When drawing Lewis structures, we have limitations in the way that we draw it on paper. We can only draw one particular attachment of the elements together. There are more than one way that we can draw Lewis structures in which the elements are attached in the same way, but the electrons move. And we call those different structures resonance structures. And because we're limited in the way we can draw it on paper, the actual molecule is a combination of all possible resonance structures. And we call this a resonance hybrid. It actually exists as a combination of those structures. So one way to tell if there are possible resonance structures is to look for multiple bonds or lone pairs. So the example of sulfur dioxide that we drew it with a double bond on between one oxygen and sulfur, but it could just as easily be drawn with the double bond between the other oxygen and sulfur. And so the actual structure is a combination of the two. Instead of it being one double bond and one single bond, it is really more like two 1.5 bonds, as electrons are freely shared in both resonance structures. It is a resonance hybrid of sulfur with a 1.5 bond to each oxygen. We can think of this kind of like hybrids of animals. So if we have two different breeds of dog and we combine them, we end up with a hybrid that has traits of both of the parents. When we draw a resonance structure, we draw, say, ozone. We draw the double bond on the left side or the right side, but really it shares traits of both, and those electrons are shared across in more like a 1.5 bond. So it's a hybrid of the possible resonance structures that we can draw. We do have some rules that we need to follow. So they have to have the same connectivity. The atoms have to be attached in the same positions. The only thing that we can change is the position of the electrons. They have to have the same number of electrons. Because of our Lewis structures, we can't bring in more or less electrons to draw resonance structures. It has to be the same number. If it is in the second row, the elements have a maximum of 8 electrons that they can use. And those include the bonding and the non-bonding. However, if it is in row 3 or below, then we can have an expanded octet. We can put extra electrons into the empty d orbital and have more than 4 bonds around any third row element. So we can have 5 or 6 bonds possible. The formal charges must also total up to give us the same amount of formal charge we would expect on the molecule, which would be 0, or on the ion, which is the charge of the ion. Let's look at drawing resonance structures. We'll look back at the example that we have previously used of nitric acid. Now, we have multiple bonds, which is our double bond to our oxygen on the right-hand side. Now, this isn't the only possibility we could have. We could also have the case where the double bond is to our top oxygen. And so these would both be possible resonance structures of nitric acid. Our formal charge would not change. The total formal charge would not change. So our nitrogen would still be a +1 in both cases. but we have different oxygens that are -1. And so these are both possibilities. Let's look at another example. So sulfuric acid, following our Lewis structure rules, we could draw sulfuric acid that looks like this, where we have sulfur in the middle. Everything has an octet. But if we calculate our formal charges, our sulfur would have a +2 formal charge, and each of these oxygens would have a -1. To draw a Lewis structure, because sulfur is in row 3 or below, we can actually move some of these lone pairs in to make a double bond. And so if we do that, and we form a double bond between the sulfur and each of the oxygens not connected to the hydrogen, we actually change the formal charges. So now, if we calculate our formal charges, the oxygens would each be 0, and our sulfur would also be 0. Because sulfur is in row 3 or below, and it can have an expanded octet, and so this would be a much better resonance structure because we've decreased the elements with our formal charge. If we add up the total, we would still end up with a 0 in each case. However, we're going to try and decrease the total of or decrease the formal charge on each element to improve the structure. So when we're evaluating our resonance structures, just as I said, our better structures are going to have fewer formal charges on the elements, or less elements with formal charges. We're also going to draw structures that have smaller formal charges. So the smaller or closer to 0 we can get for all of the elements, the better. Better structures have the negative formal charges on the more electronegative element because the electronegative element is going to want to pull any extra electrons towards itself. Here are some practice problems that you can try. See if you can identify any structures that have better or equal resonance forms and draw them. Pause the video to determine your answer. Our carbon dioxide, because of the formal charges all being 0, does not have any better resonance forms. Neither does our P2H4 because all of the formal charges were 0. However, the SeOF2, if we form a double bond between the selenium and the oxygen, that decreases the formal charges on all the elements to being 0. If we look at our nitrite, we do have possible resonance structures by moving the double bond from one side to the other, and this does not change the overall formal charge, just which oxygen it happens to be on. If we look at our phosphoric acid, we can decrease the formal charges by forming a double bond between the oxygen without hydrogen and the phosphorus. By doing this, all of our formal charges are 0, so this would be the better resonance structure. For our sulfite, we can shift and add a double bond in to the sulfur, which decreases our formal charges. So there would be no formal charge on the sulfur or on one of the oxygens. We cannot double bond all of the oxygens because we do need to have a total formal charge of -2. And so we do need to keep some of the oxygens with that negative formal charge. And then we can shift that double bond around between the structures. So we're just changing the position of where that double bond is located in the other possible resonance structure.